All right. Good morning, everyone. My name is Alper Yegin. I'm the chair of the technical committee and vice chair of the board in the LoRa Alliance and CTO in Actility. So in the next 45 minutes, I will be introducing the LoRaWAN technology to you. So the starting point of LoRaWAN is to solve a very essential problem, how to provide long-range connectivity with low power consumption. So when using a technology like BLE, Zigbee, Z-Wave, the low power element is satisfied, but nevertheless the range has been few hundred meters. Then when one wanted to have a long range, cellular has been the only choice, but it was not possible to run devices for multiple years using the cellular radio. So that's why LoRaWAN was developed to fill in this gap, and this is how we have done it. At a very high level, these are the features of LoRaWAN: the long range, multiple kilometers, and low power, being able to build sensors that can last for more than 10 years. And while doing the two, we have also adopted the use of an unlicensed band, the sub-gig ISM. And together with that and several other elements, we have achieved building networks at a very low cost. So in terms of the range, starting with the most challenging case of a dense urban area, like being in the downtown Manhattan, that's where the range of a LoRaWAN gateway is around a couple of kilometers because of the buildings and all the structure around that. Now, as you move outside from the dense urban, as the line of sight starts opening up, the range starts to climb up. So what you see at the left bottom corner is a test in San Francisco Bay Area, where the range quickly ramps up to more than 30 miles. And then with the truly line of sight, which can only be achieved when we are looking in space, towards the space, we have partners, we have LoRa Alliance member companies with satellites that are like 500 to 600 kilometers above the ground and still being able to serve the end devices on the ground with the same power consumption as you would use regularly, which is less than 14 dBm. And when we translate that to indoor with really super low-cost picocells, which are like Wi-Fi access points, it's pretty practical to reach 2 floors up and 2 floors down in a typical building. So this is what we can achieve with the radio characteristics of LoRaWAN running over LoRa. And in terms of the power consumption, the transceiver consumes only 4.6 milliampere for receiving and 25.5 milliampere for transmission at 14 dBm. And through that, we can serve use cases like water meters and gas meters where there's no power supply. They operate on batteries, and they're able to do so over 10 years, which is a typical case needed by the utilities. So you can think of it as like your garage door opener, the same amount of power consumption, and these devices can last more than 10 years, given that if they were to send few frames a day. And what's under the hood is the LoRa modulation. That's the physical layer. LoRa modulation is based on a chirp spread spectrum, a technology used in the radar as well. As such, it has very high immunity against interference. It can be used to communicate even below the noise level, down to minus 20 dB below the noise level. And that gives us a lot of resiliency when using this unlicensed band. And recently, we have also adopted another modulation called LRFHSS. This is the long-range frequency hopping spread spectrum. What is special about this is instead of transmitting the frame at the same frequency, the transmitter chops the frame into smaller chunks and spreads them across multiple different channels. And the receiver, which is the LoRaWAN gateway, would listen to all those different channels and then would reconstruct the frame. That not only brings even further resiliency against interference, but also provides a way to use narrower band, which is very essential, especially when using satellites. So those low Earth orbiting satellites would be flying 600 kilometers above the ground and would have a spotlight, which is their coverage of more than 3,000 kilometers. So there will be way too many devices fall under that coverage, and the only way to pack so many devices under the coverage of a single gateway is to use a narrower band, and that's what LRFHSS achieves. Another very unique feature of LoRaWAN is the collaborative radio, so-called microdiversity. So when using other radio technologies like Narrowband IoT, LTE-M, 5G, Wi-Fi, the end device or UE or mobile terminal, whatever you call it, when it makes a transmission, it's only received by a single base station within the coverage, because there's an association or an attachment between the end device and a single base station. Even if there might be 2 other base stations within the coverage, they would not be tuned in to listen to those frames. Whereas with the LoRaWAN, our attachment or association is not between the end device and the base station, but it's between the end device and the network server. As such, any one of the gateways that's within the physical reach of the end device would be demodulating or receiving the uplink frames. And as in this case, 3 gateways are within the reach, and they would all receive a copy of the uplink frame. They would send those to the network server, which would deduplicate them and send a single copy to the application server. So that brings, once again, a very high resiliency and reliability to the network deployment. Imagine the changing RF conditions because maybe the device is just turning around the corner or a truck pulling over in front. Any of these changing conditions can still be dynamically accommodated without having to scan and attach to the network again with this microdiversity feature. And leveraging that microdiversity feature, we also have a feature called LoRaWAN Geolocation, having 3 or more gateways scattered around that can demodulate the same uplink. And knowing the geolocation of the base stations, plus having a fine timestamp, nanoseconds granular fine timestamping on the end device, we are able to resolve the location of the end device without relying on Wi-Fi sniffing, Bluetooth beaconing, or having a costly and battery-hungry GPS receiver on the end device. So just by carrying out the regular transmission, we're able to get the location of the end device between 20 to 100 meter accuracy, which is not something you would use for looking for your lost key, but clearly you can use this for like pet tracking, tracking people in large area, or tracking cars or machinery in the field. And the adaptive data rate, that's also one of the features that sets us apart from other competing technologies like Sigfox. The idea behind that is whenever the device is close to the LoRaWAN gateway, through the link layer signaling, it detects this proximity, and then it's instructed by the network to use higher transmission rate and lower transmission power. And then, as the device drifts away from the network, once again, the network would instruct the end device, now is the time to increase the transmission power and lower the data rate. So through that dynamic nature, the device can adapt to the changing RF conditions to preserve battery. That's a big plus, because as it gets closer, the higher data rate will consume less power from the end device, and also the lower transmission power too. And also it will reduce the interference. So for example, with the Sigfox, a device, whether it's very close to the base station or far away, it keeps transmitting at its highest transmission power and the lowest data rate, which is an overkill, right? It's like you and I were face to face and I'm like shouting and talking really slow. That's unnecessary. I can speak real fast and at a lower tone, and you can still understand me. It's the same principle. And then we get this question a lot. How do you deal with interference, right? So it's an unlicensed band. Anyone can use it. Although anyone has to comply with the regulation, for example, having a duty cycle limitation or dwell time. And then the question is, how do you ensure the network does not collapse? Well, there are several techniques we have built into our technology to deal with this situation. The first one is the chirp spread spectrum, as I have told you a little earlier, high resiliency against interference. The second one is the ISM band limitations like duty cycle and dwell time, and in some countries, listen before talk. Through that, the amount of data transmitted by the end device is limited. For example, when the duty cycle limitation says you can transmit only 1% of the time or 0.1% of the time, that means within an hour, 3,600 seconds, 1% due to cycle limitation means you can be transmitting for only 36 seconds. Then you need to be silent. So that already puts a pace on how much traffic an end device can pump to the network. So the device cannot be like streaming data. And then in LoRaWAN, we have multiple channels and channel hopping. It could be 8, 16, or even 64 channels used by the network, and the end device randomly picks one for each transmission. So we can demultiplex multiple devices transmitting at the same time, given that they're on a different channel. On top of that, even when the two devices are transmitting on the same channel, same frequency, if they're using different data rates, then the gateway can still, in many times, demodulate the transmissions. So we can even demultiplex on the same channel at the same time. If they are using different data rate, there's a way to demultiplex, demodulate both transmission. And the ADR. So as the number of devices grow, what is already happening is the number of gateways are increasing. So we have public network operators who deploy nationwide networks, and as the demand increases, what they do is they keep adding more gateways, both outdoor and indoor. And as the gateways densify, having more gateways, that brings gateways closer to the end device, and the ADR kicks in, then device starts transmitting at a lower power and a higher data rate, which further reduces the interference. So it would dynamically and organically adjust as the number of devices grow. And obviously, we have confirmed uplink and downlink, sending the end device sending a message and then expecting an acknowledgement as a confirmation, which is an optional to use feature. We don't recommend every device to use it all the time, because the downlink is also a resource that should be used wisely. But it's at the application's disposal. And the microdiversity, again, having interference on one side may not mean there's an interference on the other side, and you may be facing multiple gateways at the same time. That's very much the case whether it's a smart building deployment or a nationwide network. There's always microdiversity. It's never like one cell barely touches the other. There's always an overlap. Given the low-cost nature of LoRaWAN, organizations build network, and then there's natural microdiversity built into to any typical deployment. And forward error correction, which we not only do at the physical layer, but also it can be done at the application layer. The transmitter, instead of expecting an acknowledgement for every frame, it can build in enough redundancy into the transmissions, and then the receiving application, even if it loses any arbitrary frames in a sequence of transmission, well, obviously up to a certain level, it can reconstruct the frame with certain forward error correction algorithms. And this is something that we have built into the firmware update over the air feature as well. That way, when the firmware is pushed to the end devices, like multiple end devices at once, through several fragments, instead of waiting for an acknowledgement for every fragment, through this redundancy, we rely on the end device to reconstruct the missing frames. More on that a little later. And if we look at the end-to-end stack, this is what we have. We have an end device and the newly introduced relay, which provides an RF extension as a booster. And the stack between the end device and the gateway is pretty thin, and that's by design to make this a very lightweight architecture and also to consume as little amount of RF resources as possible. The application layer sits on the link layer, and then that has the regional parameters. The nature of the sub-gig ISM band is there is no single channel plan that's applicable all around the world. So for that reason, we have different RF regions for which we need to have some adaptation of our transport to those regions. And then below that is the physical layer, whether it's LoRa or FSK or LRFHSS. And this stack terminates on the network server, and what is behind the network server is possibly other network servers for roaming, a joint server for network access authentication and session key generation, and the application server. Now, what had started as a single protocol called LoRaWAN running between the end device and the network server became a full end-to-end architecture, as you see here. So when you hear people talking about LoRaWAN, by now it's a full end-to-end architecture, not just a single protocol. If you go back, say, 4 years ago, 5 years ago, LoRaWAN would be just one protocol. And then we have several specifications. These specifications are available through the resource library. The link layer specification is called TS1, technical spec number 1, and the backend interface is technical spec number 2. Backend spec is what runs among the application server, join server, and the network server. And we have numerous others like fragmentation, multicast, firmware management, IPv6 over LoRaWAN, so on and so forth. And then we have regional parameters. They have the abbreviation RP. And we have technical recommendations with the abbreviation TR. And then among these, our link layer spec is also republished by ITU as an ITU standard, ITU TY.4480. So this specification is the same as our layer 2 spec version 1.0.4. So we have the endorsement of ITU for our standard as well. And if we look at what's inside the regional parameters, given the regulatory differences among regions like US, EU, Japan, India, we have different sets of parameters that are agnostic to the link layer spec we have. That's why these parameters are defined in a separate document, regional parameters document. So things like what channels are used for the join, these are called default channels, and the duty cycle and dwell time requirements, the data rate supported, the data rate backoff table for the ADR, the transmission power, join accept channel frequency. All of these are defined in this document. And right now we have all these regions. So EU, US, China, EU has 433, which is not really used that much, Australia, etc. And as you see, it's not one per country. We try to aggregate countries as much as possible under a region. And that region may or may not be aligned with the continents, but it does. It's a grouping of channel plans that can be harmonized. So, for example, AS923 is a plan that's used in the APAC region. Multiple countries are under that. And then we also have some country-specific ones like South Korea, India, Russia. And whenever a new country we would like to support, we look at this table to see if we can adapt that country to an existing channel plan to reduce the fragmentation. And only if we cannot find a way, then we end up defining a new channel plan. And this is the network stack once again, the physical layer, the link layer, and right above that, today, majority of the deployments have their own proprietary application layer or applications riding right over the LoRaWAN link layer. And recently, we have adopted IPv6 to run over LoRaWAN through IETF's SHIC RFC. And through that, now we're also able to run IPv6 over LoRaWAN end-to-end. But obviously, that doesn't mean that you can do like video streaming, browse the internet, listen to Spotify for the duty cycle limitations and other regulatory limitations. So still, the application developer needs to be very cognizant of the limits of the regulations and use IP over LoRaWAN in a more constrained way. But nevertheless, it's end-to-end IP, and it's IPv6. And through that, for example, now we can run DLMS for the electric meter stack or the metering stack over LoRaWAN in a very native way. Then in terms of the communication pattern, we have three classes, class A, B, and C. So for the devices that are just doing sensing but not actuation, meaning that no need to send a command to the end device, and the device needs to have the longest lifetime with a given better capacity, we say it should use class A. What is special with class A is whenever the device wants to send a frame, it can just transmit it right away. The media access control is called Aloha. You have something to say, just say it. You don't need to listen to, you don't need to do collision detection, etc., although that's one of the new features we're working on. The device does the transmission, and after the transmission, it listens to the network in 2 time frames, and then it stops its receiver to preserve power. That's how it can ensure a very long battery lifetime, and that's why you would not want to run an actuator on that. If you want to reach the end device by sending a command, it cannot be in Class A mode, because the Class A mode, you never know when it's going to listen to you. It'll only listen after it makes a transmission. And then, if you want the device to listen to the network for commands, now at the far end is Class C. That's a mode where the device is always continuously listening. A mains powered device can always listen. So you want to control the light, the switch, or the power plug. Then you want to put it in Class C. It has mains power. It can always listen. And then it does transmission whenever it wants to, and it's always in listening mode, and you can send a downlink frame to it. And in between the two is Class B. Now, the Class B is periodic listen. So the end device opens its transceiver in listening mode on a periodic schedule. How often it does is based on the application, how reactive you want that device to be. You can configure that over the air. And the way the end device synchronizes with the network is the gateways with the GPS receiver, they sync up globally among themselves. And then they send beacons on a regular basis. And those beacons help the end device to synchronize with the network. So the device, without having a GPS receiver or a clock, can synchronize with the network through those beacons, which are sourced from the GPS receivers on the network side. And through that, on a regular basis, the device opens the receiving window, and then here's the opportunity for the network to send a downlink frame. For example, gas meters that are not only measuring the usage, but also that are instructed to shut off at the time of an earthquake, they are operating on Class B mode. So you can shut off the valves in case of any emergency, only if they're listening, and then they can do so using a battery and in Class B mode. This is the illustration of Class A. So the end device has a packet or a frame. It wants to transmit, it does so. And after that transmission, it opens 2 RX receive slots, RX1 and RX2. These are the 2 times it would listen to see if there is any downlink frames coming in. There may be a pending downlink on the network side, and the network server would know that there's a pending downlink frame. And upon receiving the uplink frame, it will use one of the 2 chances to transmit that downlink to the end device. And the frame format. I'm not going to go over this in detail. You wouldn't be surprised there's a format, right? Framing is the most essential element of the link layer in a communication stack. And just a couple of things I'd like to highlight here. One is every frame has a device address. That's how we know when the network receives a frame. By looking at the device address, it knows who the sender is. And in the reverse direction, when the end device receives a downlink frame, it inspects the device address to see if it is meant for that end device or not. And secondly, this header is bit-packed. It's super compact, because we did not want to consume too much time on air. So for that, you would see every bit counts here, and we have only just a single reserved for future use left in here. Also another one in the F-type. So you would see a design here that, unlike anywhere else, like any other communication protocol, it's very compact. And security, another question we get is, oh, you're using unlicensed band, so it must be unsecure. Totally irrelevant. Now, in wireless world, the security is not done through using licensed band or unlicensed band. It's done through cryptography. And we have a very strong cryptography. We are using AES-128, and we have all the bells and whistles of any modern-day wireless communication technology, be it 4G, 5G, Wi-Fi, the latest release. We have the equivalent security. How? We have mutual endpoint authentication using symmetric key cryptography. We have data origin authentication, replay protection, integrity protection, and end-to-end data encryption. On top of that, we have the firmware update over the air, which is our insurance. In case anything is missing or wrong in the application stack or in the firmware in the future after the device is deployed in the field, the photo feature kicks in to do a software and firmware update over the air without having to go and reclaim the device. And then, on top of that, we also have the hardware level security. Equivalent to having a SIM-based security, we're able to use secure elements on the end devices to safeguard the cryptographic keys and procedures, and these are tamper-proof hardware with the equivalent security of a SIM card running on the end device. And a counterpart of that on the network side is the HSM, hardware security module, that stores the keys in an appliance, a dedicated appliance, to safeguard the key and all the cryptographic procedures. That's equivalent to what you get with the mobile networks today, the cellular ones. So the credentials are, we use a symmetric key cryptography. On the end device, we have the device ID, a globally unique ID, a 64-bit ID. And it also knows the authentication server's ID, the so-called join EUI, which points to a join server. And the app key, that's the master root key. Now, I'm just using the LoRaWAN 1.0 to keep it simple. In 1.1, we have 2 root keys. But for simplicity, I'll stick with 1.0 security. And then the counterpart of that is the join server, which has the same credentials. It knows the device ID. It knows its own join EUI and the app key. That's how the whole system starts. Now, the network server doesn't have any of those credentials, neither does the application server. So in this model, there's a trusted join server. And using that, we run the so-called join procedure or the activation procedure. The 2 names are used interchangeably. That runs between the end device and the join server end-to-end, going through the network server. But network server is just a conduit here. It doesn't really get to learn the root keys. But eventually, it will learn the session key as granted by the join server. And after running this join procedure, the session keys are generated. 2 session keys. One is a network session key that is used for protecting over-the-air transmission to protect the LoRaWAN frames. And then the other key is the application session key that's used for end-to-end encryption between the end device and the application server. So the join server pushes those session keys to the authorized endpoints like the application server and network server. And the same session keys are cryptographically generated on the end device. And using these, now we're able to fully protect LoRaWAN frames. The application payload is taken in, and then using the AES CCM star, it's encrypted with the APS key, and that becomes an encrypted payload, which can only be decrypted by the application server and the end device itself in both ways. And then the rest of the frame, including the device address, which identifies who the sender or the receiver is, and the frame counter, which brings in a replay protection as it keeps bumping up in each frame, is used with AES CMAC and network session key to generate the 4-octet message integrity code, which is like a signature. And the receiving end, whether it's the network server or the end device, by inspecting the MIC against what it computes on its own using the network session key, can verify if this frame was sent by the legitimate end device. And it was not replayed, it was not spoofed, no bits were flipped en route. So it's just usual, typical wireless security. And then this is how hardware security kicks in. The device manufacturer, if it chooses to build high-end devices with high-end security, it would work with a secure element vendor. Secure element is a chip inside which there's the device ID, there's the app key, and all the cryptographic generation procedures. Now that gets soldered on the end device by device manufacturer without really knowing the root keys, and shipped to the field. On the other side, the secure element manufacturer also worked with a joint server operator and shares the device credentials using a secure channel. And those keys can be stored in an HSM, that dedicated hardware appliance. And that's how we ensure none of the gateway, network server, application server, and even the device manufacturer knows the keys. And then we can have full end-to-end security with the benefit of using hardware level security. Again, this is for high-end security. It's not necessary for all use cases. If you have a temperature sensor here, you would not really put a secure element in it. There's an additional cost with that. But if you are running, say, a gas meter, you may consider using this, because gas meter is like a cashier's machine. It's printing money every month. You may be more concerned about any tampering, and then you can consider using a secure element in the gas meters. And the firmware update over the air, we provide a secure, reliable, and efficient way of achieving this. How is it efficient? We rely on physical layer multicast. So we take the firmware file, it's just a large file, we chop it into fragments, and then we push these fragments to a fleet of devices. Instead of sending the firmware to every device one at a time, which would multiply the amount of firmware file that's transmitted, we transmit it once over the air by setting up a multicast group, getting a fleet of devices, like thousands of them, join a multicast group, LoRaWAN link layer multicast group, and then synchronize them over time with class B or turn them into class C. So they're all listening at the same time. Then transmit a single frame that gets consumed by the whole fleet. And then we keep doing that until the end, and then the devices would reconstruct the whole firmware upon the single transmission of the whole firmware. And then obviously there might be some devices that are missing some of the frames despite we are using forward error correction. Then those individual devices would notify the network saying that I'm missing this or that. Then we would either set up another group and then just push the common missing frames, or we will unicast those missing frames. And it's a whole lot more efficient than what you can do with like cellular and Wi-Fi, where the firmware is sent like 1,000 times for 1,000 devices, which takes up a lot of air resources. And well, obviously, the photo procedure is secure. We use signed firmware. The frames are integrity protected. And we ensure nothing gets modified in flight. And also, the photo is a security feature. Like I said, it's our insurance to patch something in the field in case anything goes wrong on the application stack or the firmware. And due to the very low-cost nature of LoRaWAN and the unlicensed band, LoRaWAN networks are sprouting like mushroom all around the world. People are building residential networks, using it in the office, building their own network. There are campus-wide networks, city-wide, multiple country-wide networks like France, Switzerland, Netherlands, Finland. They have nationwide networks. And then there are planet-wide networks being built and operated by satellite providers like EchoStar Mobile, Eutelsat, Lacuna. These are the members of LoRa Alliance. Now, while these are growing organically, you would say just like Wi-Fi, we have something better than what Wi-Fi has. We have a way to integrate them together. This is called network unification or collaboration, but if you look at our technical specs, it's simply roaming. Our way of roaming provides us a way to integrate all sorts of networks, small and big, all around the world, not only on the ground, but also in space, the satellite-based ones. There are nationwide networks that have set up roaming among themselves. And then there are networks within the same country with complementary coverage and even overlap coverage. With the microdiversity, we have this additive effect. And then we have roaming set up between terrestrial and satellite networks. And these flavors are all available today and being used effectively, as we speak, among public, private, and community networks. So we have practically every combination, and that's one of the power of LoRaWAN. It's low cost, it's accessible, it's open for all sorts of innovation, and it's collaborative by the technical design and also the nature of the ecosystem is very collaborative. So using roaming, we clearly provide coverage extension. That's the traditional understanding of roaming. But on top of that, something very unique to LoRaWAN is we also provide coverage densification. Because of the microdiversity, multiple gateways receiving the same uplink frame, those gateways may belong to distinct network operators. And if they have roaming agreement among them, no matter who receives that uplink frame, as in this case, there's a red, blue, and black network. The red one is the home network. Black and the blue are the visit networks, and gateways from each are receiving this frame. They all transmit the frame to the home network, which does deduplication. And what you're seeing is an additive effect, like 3 networks with their overlapping coverage acting as one. And through that, again, the ADR kicks in, densified network, so the device can transmit at a higher data rate, lower transmission power. The device battery life extends, interference is reduced, network capacity increases, and the geolocation is improved because now there are even more gateways receiving and placing fine timestamps. So everybody wins out of that. The home network, the end device, the user, all the roaming partners. It's a multiple win-win-win situation. This is just showing the message flow, how an end device joins while roaming. When the end device sends a join request, the activation, the visited network with consulting with the join server discovers who the home network is and forwards that join message to the home network server. So in addition to playing the centralized authentication server, join server also plays the role of home network discovery. And then after the join procedure, this end device is assigned a device address, which embeds the home network ID such that when it sends the next uplink frame, the visited network inspects the device address to find the home network ID prefix, and then that's how it knows where to forward this uplink frame to. So that's how we simply achieve roaming. Much, much, much simpler than what you would have seen with Wi-Fi or the cellular architecture. And the relay feature, even though we have a long-range capability, obviously the physics has its limits, right? No matter what we do, there will be a time where the end device is outside the reach of a gateway, whether it's behind like way too many walls or a very thick wall, or whether the signal had to make a turn, or if it's a satellite that cannot provide indoor coverage, there'll be a limitation. And that's in order to address that without having to put more LoRaWAN gateways, we have defined relays. These are small form factor devices that are better operated, and they use client chip to be a low-cost element to provide coverage extension. So whenever the coverage range falls short, and you want a low-cost way to extend that, LoRaWAN relay comes into the picture. And that's a very recent, we have published this spec around 4 months ago, and now we have a running demo of that at the marketplace. You can check it out.
That's in place now?
Yes. There's a demo at 2 p.m. today. And so the way to make it work with a relay, a better operated relay is the relay does not listen to the frames continuously. Instead, it has this channel activity detection window, and the end device has a wake-on radio signal to wake the relay to listen more. And the wake-on radio with a longer preamble hitting on the channel activity detection window of the relay wakes the relay up, and then after that, after sending back the wake-on radio acknowledgement, now the end device and the relay has a rendezvous, a time and a channel to meet to receive the frame from the end device to the relay. And then relay turns around and forwards that message to the network. That's the uplink. And in the downlink direction, the network sends a downlink to the relay encapsulated frame, and the relay decapsulates this, decapsulates the inner frame, which is meant for the end device, turns around, and transmits that to the end device at a newly defined receive window called RXR. Now, we had RX1, RX2, but RXR is a larger value. It's 18 seconds. The reason is this RXR needs to accommodate the transmission of the uplink and reception of the downlink between the relay and the network. And we made RXR larger than the largest RX2, so there's a chance to transmit, there's a chance for the relay to transmit the downlink to the end device. Oh, that was in the FOTA one. Here we did not really mention multicasting. I think your question sounds like a FOTA or a multicast question, not a relay one. The relay one, what I've shown is a unicast. Single frame from the end device going to the relay, from relay to the network, and downlink is single message. There's no multicast in this one.
Yeah, but if you have units that cannot listen to the answer. Yeah, if you have like multiple units not being able to access the main station, how does this multicast work with them? Because if you're sending like a multicast message, all these units cannot listen to it, cannot
okay,
receive it.
like I said, there is no multicast in this. There's no multicast. These are all unicast. The network, the end device sends a unicast, single message to the relay. Relay takes that and sends a unicast to the network. Okay. And then the reverse, the downlink is also unicast from network to the relay, which is unicast to the end device. There's no multicast in this.
So it should be like only one unit connected to a relay?
No, that's not what it means. That means one unit sends a one message received by one unit. There can be like maybe 5 or 10 end devices doing the same thing in parallel with each other, but they're independent. When we talk about multicast, we're talking about the group of devices receiving the same frame. That's multicast.
Yeah.
So relay is for unicast.
So it's one end device, one relay?
No, not that. There can be 5 end devices repeating what I've shown you. 5 end devices going through the same thing. It's.
I think what you're asking is, can those devices ever get a multicast update or anything?
No. Yeah, we do not support multicast with relay at this point.
So they'd have to move outside the relay boundary to be able to update.
Right. Today, this relay feature and the multicast doesn't work together.
Okay.
And what we do is we try to keep things simple and do one thing at a time. In the future, we will be working on multicast with relay, but today it's unicast-based relay. All right, so IPv6 over LoRaWAN, end-to-end stack. The SHIC is the static header, static context header compression fragmentation, RFC 8724 and RFC 9011. Now that gets implemented on the application server to decompress compress the IP layer to pop the IP frame and then run as an IP router towards the internet. And that's how we achieve end-to-end IP. And the application payload codec is, the codec is a piece of JavaScript code that can translate binary encoded data to JSON and vice versa. We use binary over the air for compact transport, and we need JSON for human readability and machine processing. By standardizing the API between the application codecs and the application servers, now device makers can build the codec for their applications once and run it on any application platform from any vendor as long as this recently published API is used by both the device maker and the application platform. So we bring portability to application codecs through this API. Well, okay, that's that. So if you would like to know more, please visit the resource library. You can download our technical specs, technical recommendations, FAQs, and webinars. And if you're not already a member, I would obviously highly recommend you join the LoRa Alliance, join the technical committee and the task forces, and join this. Join us innovating and disrupting the field and solving problems that could not have been solved in the past. Thank you for listening.
I have a question about the application codec API. So I was about to ask if the Alliance was going to develop application profiles similar to the way that USB or Bluetooth have. There's a standard mouse and a keyboard, and any manufacturer complies with that application format. So it looks like the application codec API is a slightly different approach where each manufacturer publishes the codec for their application. But is there still any plan to make profiles for devices so that anyone, you don't have to constantly update your database of codecs, and you can just have, interoperable temperature sensors that you can take from any vendor, and it'll just work because it's the same application protocol?
Right. So as you see, we are at the edge of the network connectivity and application domain. We take one extra step to make the ecosystem life easier by building this. Now, there are multiple steps ahead of that, including like building application profiles or even identifying a common taxonomy for like harmonizing how various data elements are represented, things like that. Now, the challenge with that is it's a really big piece of work. The applications are there's so much variety. It's not like running a smart home. We're not in just smart home domain. We are in every domain. Like there are 7 verticals, and there's like gazillion different applications. Trying to provide a standardization for the application domain. It not only falls outside our realm in here, and also it's a big fish to fry. Now, that doesn't mean that we'll never do that, but we're eyeing opportunities to, instead of like defining it within the alliance, identifying where they're defined and then pointing to external standards would be much more scalable than we taking up this boil the ocean activity. It's absolutely necessary, and then we're taking one step at a time. It's in our radar, but not in the near horizon.
Thanks.
Yes?
You said 2 o'clock. I don't see it on this list.
It's not on the list, actually. It's at the marketplace, and it's run by Semtech and Actility. You would need to go to the Actility's table to see that demo. That's the relay demo. Yes?
So if you have a relay that's on mains power, theoretically, could you have that device be both, it is an end device, as well as a relay for some other
Yes.
end device?
No, even without the mains being mains powered, even as a better powered, it is actually an end device on its own. It's also relaying for other devices. It has this dual functionality.
Excuse me.
Yeah. Let's use the micro. And regarding the time, I have one other session right after this. Anyways, I'm eating my own time anyways, sir.
Yeah, my thought process was just that that device would be Class C, so it's always powered, and then you would have another Class A end device that's using it as a relay, but that Class C device is also its own end device. It has sensors and stuff.
That is true, but that could also be a Class A device itself.
Okay, fair enough.
So a battery-operated relay would, from the network point of view, it would be seen as an end device and a relay.
Yeah.
It can have like sensors and do its own thing while also relaying for the other end devices.
Yeah. So effectively, you can daisy chain them in a sense.
Yes.
Yeah.
All right. Any other questions? Yes, go ahead, please.
If I have a Class A device, but I want to do almost a if-then. So a Class A that sends a message, but then I want it to listen for 8 hours, because I may want to send a command over that 8 hours rather than the
good
R1
question.
and R2. Is there a way to schedule that?
Yes, absolutely. By definition, every device is in Class A, and on demand, it can add Class B and Class C for a period of time. So you can be Class A to preserve energy, and say all of a sudden you would like to be in a more listen mode, right? Depending on your battery budget, you can be Class A plus Class C and always listening, or Class A plus Class B, like listening periodically. That's exactly what we do with the FOTA. Say there are like 1,000 devices in here, they're all Class A. Now I want to run a campaign, a FOTA campaign. I tell these 1,000 devices, listen, I'm going to be sending you a bunch of frames. Get on Class B now, or get on Class B 10 minutes later, or at 1 p.m., right? They switch to Class B, they're all listening, they're all ears. I push, and then at the end, I tell them, okay, now you go back to Class A. So you switch, not switch, but add other classes. But you cannot be Class B and Class C at the same time. It would not make sense. Why would you do that, right? It's A plus B or A plus C.
Okay. Is that handled at the application layer? Application server?
In 1.1, there's a link layer command to do that switch. In 1.0, it's done at the application layer. Now, if you look at the FOTA specification, for example, the FOTA signaling does that in its own messages. The FOTA message says now, at this time, switch to class B. So in a sense, it's an application layer, but it's defined by us. So you would have to do the same equivalent in your 1.0 device. Or in 1.1, there's a way to do that over the air using a MAC command.
Okay, thank you.
Thank you.
I had a quick
one
question, real quick question.
one last question,
So
then-
that relay function, is it a single Samtec chip to do the entire relay function, or does it require 2 radios and a microcontroller?
No, single
Okay.
radio.
And do you know that part number off the top of your head?
I'm sorry?
The part number? The Samtec part number?
Find a Semtech person.
Okay,
please.
sure.
Yeah. Okay, all right, so thank you for listening, and feel free to ask any questions in the hallway, and me, and also we have TC members here as well. So thank you.